Bismillahirrahmanirrahim. Assalamu alaikum, students. So let us start today's lecture. Now, in today's lecture, our topic is let me write it first, density of distribution in the phase space let me change the color, let me underline it. Then I will write here averages for the ensemble. Averages for the ensemble. This is our today's topic. In the previous lecture, we discussed the idea of phase space. We said that the state of a classical system having f degrees of freedom is specified by specifying its f coordinates, generalized coordinates, and corresponding f momenta, and we can construct or conceptualize a 2f dimensional space called phase space, which will have one rectangular axis corresponding to each coordinate or momentum. Then we said that a point in such a phase space at a particular time will specify the state of the system. So if the system evolves in time, that means if its coordinates and momenta change in time in accordance with Hamilton's equations of motion, which are laws of mechanics, then this point will move in the phase space. That means its states will change with time, right? And we said it that the position of the phase point representing some system in the phase space at a particular time is complete information. If we know its position at a particular time in phase space, we can predict its trajectory in future. That means we can predict using laws of mechanics how it is going to evolve in time, and we can also predict where from it has come and reached that particular state using laws of mechanics. Then we talked about the idea of ensemble. We said if we have some system of interest and we want to describe that system, as we talked about the oxygen gas inside that container, when we took 32 grams of oxygen in that and we said if the molecules are freely moving, then we will have 6Na coordinates required, where Na is the Avogadro's constant. We require 6Na coordinates. 3Na will be pertaining to position and 3Na will be pertaining to velocity to specify the system at a particular time. And this number is huge. We cannot digest this much information when we use laws of mechanics to describe the system. And this method we call microscopic method. So this microscopic method involves a lot of variables and describing the system in terms of those variables becomes uh, very difficult, almost impossible, because of the number of variables involved is very large, right? Then if we take into consideration the rotations of these oxygen molecules, or you take the vibrations into consideration, then the number of variables will further increase. Then we said we can characterize the system in macroscopic terms. We specify some macroscopic quantities and specify the macroscopic state of the system. The advantage is that the number of variables which specify the macroscopic state is small. So handling these small number of variables is easy to specify the system, and we can predict the system, the properties of the system as a whole. That is what thermodynamics does. Then what is the issue? Issue is that when we use this macroscopic method, we use these macroscopic variables to specify the system, state of the system, we are disregarding the internal details of the system. Then what is the bridge between this microscopic situation and macroscopic situation? That is the statistical mechanics. Statistical mechanics does what? It averages over all these microstates the behavior of the system. Then when we average over all these microstates, that average we correspond to the average behavior of the macro state. Now in this regard, we define an ensemble, that we also discuss, that if we have some system of interest which can live or exist in many microstates, then what we do, we conceptualize a collection of identical systems, right? This collection of identical systems pertaining to some system of interest is called ensemble of systems. Now, what statistical mechanics does, it conceptualizes this ensemble pertaining to some system of interest. Then to find the average value of some quantity of the system of interest, we average over all these systems in the ensemble, and that average pertains to the system of interest, right? Then we discussed, when we use this idea of ensemble in the phase space corresponding to each system in the ensemble, what will happen? Corresponding to each system in the ensemble, we will have a representative point, and corresponding to ensemble of systems in the phase space, we will have a cloud of points, right? Now the situation of the ensemble at a particular time will be specified by that cloud of the representative points, one point pertaining to each system in the ensemble. Now, in this regard, what we do, since we have large number of systems, that means we have large number of separate members corresponding to ensemble, our collection of systems is large, population of systems in the ensemble is large. So what we are interested in this thing, that what is the number of systems pertaining to the ensemble of systems at any time, which would be found in the different states that correspond to different regions in the phase space. I repeat, we are interested in the number of systems in the ensemble at any time, which would be found in different states that correspond to different regions in the phase space, right? Now, since the number of systems in the ensemble is large, therefore these numbers of systems at any time, which would be found in different states, these numbers can be treated as continuous numbers. because the population of systems in the ensemble is large. Now, what we do, the condition of an ensemble at any time, therefore, can be regarded as appropriately specified by the density function, right, with which representative points pertaining to the ensemble are distributed over the phase space. So we define the density function. Let me write. I will choose another color. Let me use this blue. I want to increase the size of my line in the pen. I will use, I think, this one, thick. So we define this density function rho. So this rho is, in general, the function of all Q's, Q1, Q2, up to Qf, and all P's, P1, P2, up to Pf, and time in general. So let me name this one. What is this rho? This rho is actually giving us the density of representative points, that is the systems in the ensemble distributed over phase space, right? Now, in this is the system, we are taking the system having f degrees of freedom. So the condition of the ensemble in the phase space at a particular time will be mathematically described by this density function, because this density function will give us that picture how different systems in the ensemble of the system are distributed over the phase space. That means how they are distributed over different states in the phase space. So this represents mathematically the situation of the ensemble in the phase space. Now, in abbreviated form, I can just write this rho as rho, we write it just rho of Q comma P comma T. So let me name it second. So this Q represents all the Qs, and P represents all the P's, T is in general time. Now let delta N be the number of systems which would be found, which would be found at time t, to have the coordinates and momenta lying in any selected infinitesimal range, let me write it clearly. It is infinitesimal infinitesimal range. I will change here color. What range? Delta Q1, this is product here, up to delta QF, then delta P1 up to delta PF. Understand it, this is a volume in phase space which has extensions along Q1, delta Q1 along Q2, delta Q2 along Q3, delta Q3, and similarly for all the coordinates and momenta. Now, question is, if delta n is representing number of systems which would be found at time t to have the coordinates and momenta lying in any selected infinitesimal range, which I have specified, then in other words means the number of systems in the ensemble which would have states at time t, that states are lying in this volume which we are considering. Then how we can express this number? It is simple. We have to multiply the density function with this volume. So let me write. First I will add page to my board. So I should write then my delta n is equal to rho of QPT times the volume which is under question, delta Q1 up to delta QF times delta P1 product up to delta PF. So I name it as 3, right? Now, if I integrate over the whole phase space, let me write it. By integrating over the whole phase space, we can write therefore n equal to integral. See, these are many integrals. Let me first write it, then I will explain. QPT times dq1 up to dqf. Then you have dp1 product up to dpf. Name it 4. See, we are integrating equation 3 over whole phase space. It is understood. If 3 is giving me the number of systems which at particular time are lying in this infinitesimal volume, delta Q1, delta Q2 up to delta QF, delta P1 up to delta PF. If I integrate over the whole phase space, that means if I add these number of systems in different regions, I will get the total number of systems in the ensemble. Now, when I am integrating these intervals, dq1 become infinitely small. They become delta q1 becomes dq1, delta q2 becomes dq2, and similarly delta p1 becomes dp1. Now, this integral here means I have to integrate first over dq1, then integrate over dq2, then integrate over dq3, and similarly up to dpf. So here, when we are writing this integral dot 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 integral, it means there is a product, there is a series of integrals, right? It's a multiple integral. So n here is now, n here is, let me use this color, x. So n is the total number of systems, total number of systems in the ensemble which is under consideration. Total number of systems in the ensemble, or phase points into phase space, right? Now it is understood that for the physical interpretation of this formalism, it is essential that the integral in equation 4 for n should converge, must converge. We will be dealing in general and or concerned in general only with densities rho which have this property that n converges, right? So let me first throw some light on rho. See from figure 3, sorry, figure 3, not figure 3, equation 3. In equation 3, if you interpret rho, what is rho? Delta n is the number of systems contained at time t in this volume. Delta q1, delta q2 up to delta pf. That means if I have to interpret from 3 rho, it is simply the number of systems available at time t in unit extension. That means the volume which has unit length, all these delta q1, delta q2 up to delta pf. We call that unit extension. Unit extension means this volume has all edges with edge length 1. So if I make this volume 1, rho becomes equal to delta n. That means I can interpret this density from figure 3, this density, equation 3, sorry, this density function as the number of systems contained in unit extension, that means unit volume in phase space at a particular time, right? Now let me move further. If I write, I think I will write that in next page. Now if I write from 4, we have what? If I divide this function rho of QPT, I divide it by n, the total number of systems in the ensemble, which can be written as rho of QPT. Then I divide that by this multiple integral, which is n rho of QPT times dq1 up to dpf. I name it equation 5, right? Now I have to interpret this ratio. I am dividing this density function by the total number of systems in the ensemble. Now I want to interpret it. Think about it, what it represents. For a moment, you can think about it. This gives me, this ratio gives me what? The probability. I will write it, you think about. Is gives me probability per unit extension, per unit extension. By extension, we mean the volume in the phase space. In the phase space, in the phase space, that the phase point is representing the system in the ensemble, that the phase point for a system, for a system chosen at random, chosen at random from the ensemble, from the ensemble would be adjust it, would be found at time t, found at time t to have the specified, to have the specified values of the Q's and P's. Understand it. I'm saying this ratio, if I divide this row by n, and where n is the total number of systems in the ensemble, rho is the number of systems in the ensemble in unit extension, that means in unit volume of the phase space. So if I divide rho with n, I get the probability per unit extension in the phase space that the phase point for a system which you chose at random from the ensemble would be found at a particular time t to have the specified values of q's and p's, right? You think about it, it is easy, because when you are finding the probability, we see the favored outcomes of the event, then we divide by the total number of outcomes. Think about it. Now, rho is the number of systems in unit extension. When you divide it by the total number of systems in the ensemble, it becomes probability. Probability of what? That you will find some phase point, that means some system in the ensemble at some time t to have the state specified by some q's and p's in some zone, some unit extension, which is under consideration, right? Now, if you use this further, we can find the average value of some mechanical quantity pertaining to the system, or which characterizes the system or systems. Systems means we are considering the ensemble under consideration. We can find its mean or average value by a simple equation. Let me add page to this. So I will change the color of writing. So if, let me write this way, let f of qp, function of all the q's and p's, be a mechanical quantity some mechanical quantity in general which characterizes which characterizes where am I am here which characterizes systems of the kind which is under consideration under consideration its mean value or average value for all the systems in the ensemble, for all the systems in the ensemble would be given at time t by at some time t by. So I write it this way, f of qp bar is representing here the average value. It will be 1 by n, then this multiple integral write it this way, this multiple integral, then I have f of qp, then I have rho of qpt, then I have the volume element dq1 dq2 what dpf, or I can write it this way also, this multiple integral again f of qp, then rho of qpt, then I have this dq1, sorry, this dq1 here, dq1 of dpf that I write, and in terms of the integral itself, I write it as a multiple integral rho of qpt, then dq1 of dpf. I name it as equation 6. Think about it. So if I have some mechanical quantity which characterizes the systems under consideration, that the systems in the ensemble considered, then its mean value over all the systems in the ensemble, or for all the systems in the ensemble at particular time, will be given by this expression 1 over n, then this multiple integral, then you multiply this function within the integral with the density function, and then you have to integrate over all q's and p's. It's a multiple integral, or you can use the definition of n in the denominator and write this also as a multiple integral, right? So this is how we find the average value of any mechanical quantity over all the systems in the ensemble. Now, there is another way to interpret the density function. See, sometimes we normalize rho to unity. Let me first write it, then I will understand, make it clear to you. So instead of taking the quantity rho, precisely as above, which we have defined as above, it is sometimes convenient, convenient to regard it to regard it as normalized to unity. Understand it as, let me adjust it, as normalized to unity. In accordance with the relation, in accordance with the relation which relation with the relation this multiple integral rho of qpt, then we have this, we write it clearly, dq1, then this is up to dpf. We normalize this thing, we write it equal to 1. Dynamic equation 7. Oh, it's not okay, it's okay. This equation 7, see, this is the normalization situation. This equation 7 sometimes we call the condition of normalization. See, if you have a dice, you know this dice has 6 outcomes. If you throw it, you can get uppermost side can have 1 on it, or 2 on it, or 3 on it, or 4 on, or 5 or 6. Now, if you are asked the probability per outcome, what is the probability of getting 1 as the uppermost side, you say it is 1 by 6. Probability of getting 2, it is also 1 by 6, and similarly you find these individual probabilities pertaining to 6 outcomes, right? Now if you are asked what is the probability of getting any of these outcomes, any of these outcomes means what it is understood, When you toss it, it is certain that you are going to get one or two or three or four or five or six. That means probability of getting any one of the outcome is one, because that is certain you are going to get one or two or three or four or five or six. So mathematically, what you do when you find these probabilities pertaining to each outcome, if you sum over all the probabilities of all the outcomes, you should get one. That's the meaning of normalization. Because you're sure that you are going to get any one outcome out of one, two, three, four, five, or six. So probability of the first outcome plus probability of second outcome, that is 1 by 6 plus 1 by 6 plus 1 by 6. When you add it, all the six outcomes, 1 by 6, six times, you will get one. This is the normalization condition. So one way of defining rho is the previous situation. Let me move to the previous slide. One way of defining rho is using equation 3. When you use equation 3, then your rho here represents the number of systems in the ensemble which are available in unit extension, unit volume. In equation 3, rho represents the number of systems in unit extension or unit volume. But if I use this equation 7, I normalize the situation, then rho is giving me what? It is giving me probability per unit volume. Probability of finding some system in the ensemble in unit volume, not the number. Because when you multiply this probability per unit volume into this volume under consideration, then you add over all the situations. That is the normalization for probability, right? So sometimes you define that way, that is using equation 3, or sometimes you define using this equation 7. So you normalize rho. When you normalize rho, you have to interpret it accordingly. So here I will make it clear. When I normalize it, let me first change color. I will write it using green. So here, this rho, when it is normalized, then what it is representing? It gives directly the probability, per unit volume of finding the phase point for a system, phase point for a system, picked and random, picked at random from the ensemble, from the ensemble in different regions of the phase space, in different, let me adjust my pen, in different regions of the phase space Let me write it clearly. I will add page to it. Where is this undo function? I will complete it here. In different regions of the phase space, in equation 7, it directly gives you the probability per unit volume of finding the phase point for a system in the ensemble which you pick at random from the ensemble in different regions of the phase space. And when you use this definition of rho to normalize it to unity, then this expression for the average value of the mechanical quantity F will simplify because the denominator in this equation 6 will become simply 1, right? So let me add page. Therefore, my average value of the function will be simply given by this multiple integral rho of qpt. You multiply it with the function fqp, then we have this volume element dq1 up to dpf, and name it 8, right? So both ways we discuss the situation, but once you define rho, which way you are defining it, you have to track that, you have to check that and interpret your expressions accordingly, right? So here we completed our lecture. I will summarize the lecture first, then I will see, I may give you homework. So we were discussing the density of distribution in phase space function rho and how to find averages for the ensemble. So we said the condition of the ensemble in phase space at particular time will be specified by a density function. Then we said how we can find the number of systems which would be found at time t to have the coordinates and momenta lying in some selected infinitesimal range, volume. We multiplied the density with the volume element which is concerned. Then I said if I integrate it, I will get the total number of systems in the ensemble if I integrate it over whole space, whole phase space, and keep this thing in mind. We're treating rho as a continuous function because we are saying that the number of systems at particular time in any infinitesimal range, it can attain continuous values that we can do because n is large. The population, that is the number of systems in the ensemble, is very large. So it will be a realistic situation in that sense. Then we interpreted this ratio. Then we said how we can find the average value of some mechanical quantity. The quantity which characterizes the system depends on Q's and P's. Then we said that we can use another interpretation of rho when we normalize it. In that situation, it is the probability per unit volume of finding the phase point for a system, pick it at random from the ensemble in different regions of the phase space, and the average value of the mechanical quantity concerning the system becomes simple. Actually, in the next lecture, we have to discuss the Level's theorem. Level's theorem pertains to this density function. So we were first bound to understand this density function, right? When we talk in terms of quantum mechanics, what happens? This mechanical quantity, this density function, there is replaced by density matrix. And in that interpretation, we frequently take density function as normalized to unity. That means we use the second interpretation there, right? So I will give you a simple homework, a simple question. Let me give you a question. Okay. So I will give you a homework now. Let me adjust my pen. Homework. Your homework is coin tossing problem. The question goes like this: I toss 4 coins. 4 coins are tossed, right? So when I toss 4 coins, uh, I can get different outcomes. I am interested in finding, it is understood each coin can have one outcome as head or tail. When I say head outcome, that means the upper side of the coin will be head. When I say toss this tail as the outcome, that means upper side will be tail, right? And we are excluding the possibility that when I toss a coin, it will balance on its edge. That possibility we're excluding. Now let N1, let me write it clearly. Let N1 be the number of heads, and N2 be the number of tails, which I get when I toss the 4 coins. Now, what is the question? Find the number of macro states in this system. Find the number of macro states in this system, number of macro states in this system, and the number of microstates corresponding to each macro state. Here is a hint for you. It's easy. Hint is our coins are distinguishable. We can label them. Our coins are distinguishable. That means we can label them. So we can label them as coin 1, coin 2, coin 3, coin 4. We label them Then see what are the number of macro states possible and the number of micro states corresponding to each macro state, right? Denote by n1 the number of heads which you get, n2 the number of tails. For example, I will give you the one macro state will be n1 is equal to 4 and n2 is equal to 0. This is one of the macro states. Another one will be n1 is equal to 0 and n2 is equal to 4. These are two macro states. Now you have to find the micro states also corresponding to each macro state. When I say n1 is 4, that means all the coins have heads as their outcomes. N2 is 0, that means no coin has tail. N1 is equal to 0 means all the heads are 0, so all the tails are 4. That means all the coins have tails at their outcome. This is your homework. Do it. And don't forget to like, share, and subscribe my channel. If you have any queries, you can comment. That is no issue. I will try to answer your queries. Thanks. Assalamu alaikum.